morning, everyone. Today, Conrad is going to talk about continued fractions.
All right, thank you. So continued fractions are a topic that was very prominent in the 19th century. Nowadays is not a typical topic that students learn about unless you work in number theory. Pretty much everyone has heard of continued fractions there, very important. They also show up in dynamical systems and in certain areas of physics. And I'll show you some really interesting properties of continued fractions. It's a different way of writing numbers than decimals, and they have their own special kind of advantages. So in order to illustrate this, I hope I will succeed at this task. I'm going to try to do a magic trick. So I want some people to get out a calculator or smartphone and write down a fraction where the decimal part in the on the screen is not obviously repeating. So I don't want to hear 0.877777. So I want some people, I'll pick two decimal expansions where you just give me the first 8 digits and I'll write them down, and I hope I will be able to predict which fraction you pick. Don't tell me the numerator and denominator. Keep a record of that for yourself so you can check later. So who wants to try this out? Jim?
Sure. 0.98.
Hold on. Point what?
0.98163,771.
Okay, 98163,771. All right, so I want to predict that number. So with a point, what? 98163,771. Is that right? Really? 98163,771. 98163,771. Okay. Really? 53, 25111, 25111. Whoops. Was it 1978 or 2015?
Exactly.
Now, so This is 1978 over 2015. So this is the year that Jim graduated from college, and this is this year. I know that because the gentleman in the front row wrote his senior thesis when he was a UConn undergrad on continued fractions almost 40 years ago, and I found it yesterday in the library, and I looked at it. So hopefully by the end of the talk, I'll be able to remind him what his thesis was about. Now the interesting thing about this is he gave me 1, 2, 3, 4, 5, 6. He gave me 8 digits, and it's not obviously repeating. Any fraction has a repeating decimal, but the period length of that fraction, I will compute it for you now without getting into the details. So this fraction has a period length of 30. Okay, so he gave me less than a third of the repeating part, yet I was able to figure out exactly which number it was. Okay, and so that's kind of surprising because it sounds like an ill-defined question. You give me only a piece of the repeating part, you haven't given me the full period, it's incomplete information. There are infinitely many potential fractions that start with this, yet I actually figured out the number, and we were not in cahoots. Okay? Although in retrospect, I'm not surprised at the number that you picked. So I want to explain how I did this, and so the method uses continued fractions. Okay? So all through school and in applied math and elsewhere, everyone thinks that writing down numbers concretely using decimals. Continued fractions are a completely different way of writing down numbers, and they have their own special properties. They're not easy to add and multiply, but they're very useful for finding very good approximations, much better than you can with decimals. So just to illustrate, so that here we have this kind of cute trick that I did. Why would anybody care about guessing a fraction if you only have a chunk of the decimal approximation? So here's an example of a problem that came up in pure math. So in the late 1970s, a priori proved that the infinite series of the reciprocal cubes is irrational. Okay? For those who know what the zeta function is, the zeta of 3, irrational. This number is irrational. It was known earlier, Euler had essentially shown that the reciprocal powers, even powers, there were some of the reciprocal squares or reciprocal fourth powers can be expressed in terms of some power of pi, and those are irrational. And so Aperi came along and he surprised everybody by giving a proof of the irrationality of this infinite series. And in the course of the proof, he showed that the infinite series of the reciprocal squares can be written in this way, with n squared times the binomial coefficient of 2n choose n with the coefficient of 3 up front. And the sum of reciprocal cubes has a similar thing with alternating signs and a similar denominator. The exponent has gone from 2 to 3, but now you have a funny coefficient of 5/2. So some people ask, could this type of identity be extended to further such series? And so the natural next guess is, let's try reciprocal fourth powers, and you increase the exponent from 2 to 3 to 4, and let's go back to constant numerator 1, maybe something special about even powers of 1. But then we have to figure out, to guess what number r might belong here. Is there some fraction that goes there? And you can compute this series and this series to very high accuracy and take the ratio, and you find that if there were a fraction or some number that goes here, that numerically it would be, well, here it is, the first 6 digits after the decimal, 0.2.117647, then your task is, what should that number really be? If it were a fraction, what should it be? You look at it, and you can't figure out, I don't know, just like this. What fraction did Jim have in mind? And I was able to figure it out by some method, using continued fractions I'm going to tell you about. So I'm going to show you, after we talk about continued fractions, how to guess what rational number that is supposed to be. Notice that is rational. Obviously, it's a finite decimal, but it's probably just an approximation to a true value that belongs there. So we're going to figure out what fraction ought to be there, at least to give us a good conjecture. All right? So this is a nice, interesting, I think, introduction to the idea of continued fractions, and let you do things that you wouldn't ordinarily think are really possible. And this idea of guessing a fraction, if you only know an initial decimal approximation, really has great potential application, because Shor's algorithm to factor numbers efficiently on a quantum computer actually relies on this idea. In the quantum part of the algorithm, you need to be able to guess a fraction, and all you have is a decimal approximation. And so continued fractions show up in this algorithm as an important way of guessing what a fraction ought to be. Right? So, so what are continued fractions? So a continued fraction is a probably potentially infinite expression like this, nested fractions, a1 plus 1 over, a2 plus 1 over, a3 plus 1 over, a4, and so on. The first term can be any integer. All of the denominators here, these a's, these entries after that, are positive integers. And as you can imagine, this is very annoying to write down, especially in the 1700s and 1800s, in the heyday of the subject. And so conventionally, we write the continued fraction in brackets as a sequence, but this is just shorthand for this more vivid expression. And the meaning of this infinite continued fraction, like infinite series or infinite products, is the limit of the finite continued fractions. You chop it off at a1, then you chop it off a1 plus 1 over a2, a1 plus 1 over a2 plus 1 over a3, and the limit of those truncations is the full infinite continued fraction. And when we chop it off at n terms, we call those convergence, the nth conversion. So the full expression, the limit might be irrational typically, but when you truncate it, you get just simply a fraction, once you simplify everything down. Okay. So as an example, the continued fraction expansion of pi, there's the decimal, 3.141592.6, and so on, but the continued fraction expansion for pi has this seemingly random sequence of entries. The 3, okay, then you have 7, 15, 1, 292, and so on. I'm not going to write this out in full form. You can do it in your mind. And so what are the first few conversions? The first conversion is just 3. The next conversion is 3 plus 1 over 7. There's your 22 over 7, a famous approximation to pi. The next conversion is 3 plus 1 over 7 plus 1 over 15. 3 over 106, getting a little bit better. And then the next conversion, the fourth one, 3 plus 1 over 7 plus 1 over 15 plus 1 over 1 is 355 over 113. And so this is a perhaps less famous approximation to pi than 22 over 7, but it's much better. Look at this. For only 3 digits in the denominator, barely more than 100, you have 1, 2, 3, 6 digit, 1, 2, 3, 4, 5, 6 digit accuracy after the decimal point. So this is the sense in which continued fractions, when you truncate them, they give you rational approximations that are much better than you would ordinarily think is possible to achieve for that denominator. If you took the actual decimal and tried to get a rational approximation from that, 3141592 divided by 10 to the 6th. Right? That's a good approximation, but your denominator is a million. Right? Here I can get just as good an approximation using a much better denominator. So that's the really striking feature of these convergence in the continued fraction representation. Okay? And we're going to see later on that the fact that this one is such a good approximation given its denominator is closely related to the fact that I chopped it off right before this huge 292. And this, we'll see later, is how I was able to guess this fraction as well. Where a continued fraction is a huge entry, if you chop it off, what comes before that is an especially good approximation, as we'll see later on. So here's the continued fraction for the square root of 3. And unlike pi, well, like pi, the decimal expansion of the square root of 3 looks fairly random. But the continued fraction representation of the square root of 3 is, in fact, well, not quite periodic, but eventually periodic. 1, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, and so on. So unlike decimals, which are eventually periodic only for rational numbers, continued fractions can be eventually periodic for some irrational numbers. Okay, like the square root of 3, the continued fraction representation is much more regular than its decimal representation. And in particular, the 9th and 12th convergence to this, those fractions you see there in the middle, these actually occurred in Archimedes' work when he was trying to approximate pi. He needed to use a rational approximation of the square root of 3, and out of nowhere he said, we'll use this lower bound, 265 over 153, and the upper bound, 1351 over 780, without getting into where these came from. And this might be after the fact rationalization here, but if one knows about continued fractions, these two approximations do naturally show up when you look at the sequence of convergence. How Archimedes found them might be a different story. But in any case, they do give you pretty good approximations. For a 3-digit denominator, that second one is good to 1 to 5 digits after the decimal point. Pretty good. Any questions? Okay. So here's just kind of a summary of the issue of some themes about writing numbers as continued fractions. So every number can be written as a continued fraction. Remember, the first entry is positive or negative integer. After that, they're all positive integers. Rational numbers actually have finite continued fraction representations. So I've discussed infinite ones, but we have to allow finite ones like finite decimals. And that covers all the rational numbers. And in the irrational case, when it's an infinite continued fraction, there's only one possible way to write a number. And for the purely periodic or eventually periodic continued fractions, we know which numbers those are. They're the quadratic irrational numbers like square root of 3, or more generally, a plus root d over b, where all those terms are integers, like 1 plus the square root of 5 over 2, or 7 plus the square root of 12 over 19. Okay, these quadratic irrational numbers always have repeating, eventually repeating continued fractions, and those are exactly the numbers with such entries. So I want to talk about how you compute the entries in continued fraction. If I give you a number, how you actually compute the convergence. There's the naive way. If I gave you a stacked, fraction, how would you actually calculate it? There are two ways to do it. One is much more efficient than the other. What makes them better than decimal approximations? We've seen some instances of this already. And how are some ways that these are used? So let's just write down a continued fraction symbolically and see how we would compute what the different entries are. So the first term, the a1, it's an integer that's less than the number, because it's a1 plus something positive. But the denominator, that first denominator, is an integer plus more stuff. So this denominator is bigger than 1. And so this alpha is stuck between a1 and a1 plus 1. So the a1, this integer, is the greatest integer of alpha. But then once you know a1, if you subtract it and then reciprocate, you get an expression just like what you had before, but all the terms have shifted up one place. So a2 would be the greatest integer of 1 over alpha minus a1, and so on. You can take the greatest integer of what you have, then subtract it and flip it, and take the greatest integer of that, and you can read off the entries in the continued fraction this way. So this is one method of computing the continued fraction expansion of a number. Right? If you're just given the number initially, you can at least get the first few of them in this way. There's clearly going to be some tension between like using a calculator to compute them and using maybe more symbolic methods, because like if I put pi into a calculator, it doesn't actually know pi. It just knows like pi is like 12 digits. And that's a rational number. So at some point, if you use a decimal approximation and take the continued fraction for that, versus your actual number like pi and 3.14159, at some point they're going to have to be different from each other. So if you try to compute the entries of the calculator, it's not clear at some point there's going to be a break, and how do you figure out where that happens? So we'll have to come back and address that on a practical basis. But anyway, this is roughly how you find the entries in principle. So let's take a rational number like 15 over 11. Okay? So this number here, well, here I've given you the initial decimal 1.36. So the greatest integer is 1. So the first entry in the continued fraction for 15 over 11 is 1. Then you subtract 1 and flip it, and then it's 2 point something. So the next entry is 2. Then you subtract 2 and flip it, and then you get 1.3 and so on. So the next entry is 1. Then you subtract 1 and flip it, and then you get 3, an integer on the nose. So the next entry is 3, and now you're done. This process stops. And so there we have 1 plus 1 over 2 plus 1 over 3. 1, 2, 1, 3. 1, 2, 1, 3. Okay, so this is a finite continued fraction. And in fact, this is very closely related to Euclid's algorithm for finding the GCD of 15 and 11. If you use Euclid's algorithm to find the GCD of 15 and 11, look, 1, 2, 1, 3. So the continued fraction entries for a rational number are very closely related and essentially equivalent to carrying out Euclid's algorithm on the numerator and denominator. For irrational numbers, you could think of the continued fractions like a generalization of Euclid's algorithm for numbers that are not necessarily rational. So let's talk about how you would actually calculate convergence. So the usual way you think of fractions is if I wanted to, for instance, take pi and compute its fourth convergent, there it is 3 plus 1 over 7 plus 1 over 15 plus 1 over 1. Because I can start at the bottom, right? 15 plus 1 is 16, and then add 7 to 1 over 16, and then flip that and add 3, and you get 355 over 113. Now, if I asked you to find the next convergent, you think, well, I have to start all over again. Stick a 1 over 292 down at the bottom, and go from the bottom up to the top again. So this is the naive way of computing continued fraction convergence. Every time you want the next convergent, you have to put a new term at the bottom and do the calculation all the way up to the top again. It turns out that, in fact, there's a completely different way to compute these from the top to the bottom, so that you don't have to start your work all over again. Okay? Which at first seems counterintuitive. How can you compute a fraction starting from the top? So I'll show you how. There's a nice algorithm to do this. So the idea is any finite continued fraction computed as a ratio, Pn over Qn, if you have n terms, where if you already know some of the previous two convergents, the nth numerator and denominator are your nth entry times the previous numerator and denominator plus the numerator and denominator that came right before that. So let's take as an example, here's pi, and here's 15 over 11. And what you do is you set out the entries along the top of a box, and for initialization purposes, put 0, 1, and 1, 0 at the start. Okay? Not 1, 0, 0, 1. It's not the identity matrix, like the anti-identity matrix. And so for instance, 3 times 1 plus 0 is 3. 3 times 0 plus 1 is 1. 1 times 1 plus 0 is 1. 1 times 0 plus 1 is 1. For the next entry, the next convergence, 7 times 3 plus 1 is 22. 7 times 1 plus 0 is 7. 2 times 1 plus 1 is 3. 2 times 1 plus 0 is 2. And then you can keep on going. 15 times 22 plus 3 is 333. 15 times 17 times 7 plus 1 is 106. And likewise here, and so on. So to find the next convergent, you just take that number, multiply by the previous element in this row and add that. Previous element in this row and add that. And these terms you're getting, these numbers, the p's and the q's, their ratios are exactly the convergence. So the convergence for 15 over 11, 1, 3 halves, 4 thirds, 15 over 11. For pi, we saw 3, 22 over 7. We saw these numbers before. So this is a way of computing new convergence from the previous two, as long as you give me the new an. You don't have to start at the bottom. So we're essentially going from the top down. And one thing that this shows us that's interesting is, if you look at the denominators, for instance, the first denominator will always be 1. So the first convergence is the greatest integer divided by 1. And the next term will be at least 1. And look at the recursion. This an, once you're at least 2 and up, this is always at least 1. So qn is always at least the sum of the previous two. It's like the Fibonacci inequality, where the first two terms are both at least 1. So the general nth denominator will be at least as big as the nth Fibonacci number. And those grow pretty quickly, roughly like 2 to the n over 2. And so the denominators are growing exponentially. And the numerators, you can show the same, you have a very similar recursion. And so you can show in the same way that the numerators grow at a pretty fast clip also. Maybe at the beginning it's slow, but eventually they pick up and they both grow quickly. Let's see how the convergence look. How do they approximate the number? The first conversion is the greatest integer. That's on the left. Then the next conversion is to the right, and to the left, and to the right. And so the conversions alternate being both less and greater than the number. If it's rational, at some point they'll equal the number, but in general, they'll just alternate the sides and get closer and closer. And so we have this kind of picture here. So you have to be careful with your indexing. Some authors will index the entries, not A1, A2, A3, but A0, A1, A2. So if you start the indexing at 0, then the even conversions are from the left and the odds are from the right. But the way I'm doing it, the odds are on the left and the evens are on the right. So if you see formulas in the literature with continued fractions and you see the index and you might see a -1 to the n for the nth conversion, depending on your convention, they should be -1 to the n minus 1. So you have to be a little careful about that. So this is the general picture for how the approximations bounce on both sides of the number. And because the number is always between two consecutive convergents, if we want to see how well it approximates, the distance of alpha from the nth convergent is less than the distance between the nth convergent and the next one. This is on the other side. But then if you subtract the fractions, you get a common denominator. And here you have this expression in the numerator and denominator of two consecutive conversions that's almost like a 2 by 2 determinant. If you think about how we set up the entries here, this kind of product and the difference is like going like this minus this, this minus this, this minus this. Okay? What are these little 2 by 2 determinants? Like if I start here, this determinant is -1. It's 9 minus 8 is 1. 44 minus 45 is -1. So these differences are alternating +1, -1, +1, -1. And we only care about the absolute value. So you can show in general that these little determinants are always plus or minus 1. So that numerator there is always a 1. And so, in general, the distance between alpha and the nth conversion is less than the distance, the 1 over the product of consecutive denominators. But we know that the n plus 1th denominator is given by this formula is at least as big as drop that term. It's at least as big as the an plus 1 times the previous denominator. And these denominators grow like this power of 2. And so this difference can be bounded above by 1 over, replace qn plus 1 by an plus 1 qn. You can replace an plus 1 by 1 for that matter. So the distance between alpha and the nth convergent drops off at least like the reciprocal square of the nth denominator. And from our lower bound on the q's, we see that this drops off like a power, reciprocal powers exponential function of 2. So these go to 0 very quickly. So this is how we show that the convergents really converge. They deserve their name. Moreover, if an plus 1 is really big, this is going to explain what my trick was before. Typically, you can just say the distance is at most 1 over the square of the denominator. But if the an plus 1, the first term after your nth convergent, is really big, then this distance is unusually close. And that's why, for instance, if you chop off the continued fraction for pi right before the 292, the convergent you get is especially good, the 355 over 113. Okay? And so we can apply this not just to irrational numbers, but to rational numbers. So this is how I did the trick before. Which is that if you have an unknown number with a decimal approximation, but you have a reason to believe that it should be a fraction, either because somebody told you it should be a fraction, I will guess it, or because there's some theoretical context, like with the infinite series examples, where you believe the number should be rational, how you can guess it is you expand the number into a continued fraction, and if it's a moderately sized number, there should be a huge entry. And if you chop it off there, because you gave me a 2, 4, 6, you gave me an 8-digit number that was only approximating his true fraction was within 1 over 10 to the 8th of this. And so if you compute the continued fraction, which I did before, the continued fraction expansion, 981637771, this truncated version of his true number, this is a rational number, and its continued fraction expansion is, the CF is 0153 25111 25111 33 114 2 313. Okay, now, so this is what I saw. Oh, in fact, I mean, it's up here on the computer screen, but it's probably, you can hear this. Here, I don't know if you see that here. Right here. See, I took his number, my f function as a continued fraction. So there it is. Okay? And so my task was to chop this off somewhere, and so my first instinct was to stop here at the 53, but I thought that's ridiculous, because 0 plus 1 over 1, if you stop here, that's the number 1. There's no way that he's giving me the number 1. So I looked for the next, so then I crossed my fingers, and I chopped it off at the 33. So if you look, you can see then I have my reconstructed rational number. I took the continued fraction that stopped right before the 33, and there's the 1978 over 2015. This is the previous convergent. Okay? Anyway, and so therefore I predicted his number was 1978 over 2015, and I was correct. So that's how that works. And in fact, if we go back to the example I gave with the infinite series, I said before that it was guessed based on the data from that proof of a priori that this series might be a rational multiple of this series, and you can numerically take the ratio and you get this number 2117647. You ask, what's the correct fraction for that? What should that probably be? It's probably not 2,117,647 over a million. Okay? So what should it be? Well, if you take the continued fraction expansion of this, this is it. This is it. The full continued fraction, 2811, 58,823. So drop that. It's just a fluke that has happened to be the last term. Drop that and use this, 2811, 36 over 17. So this was the conjecture. So this is how Fondieri and Van de Poorten, when they were looking at this problem, this is how they guessed that this fraction should be probably 36 over 17. And then once they had the right guess, then they hunted around and they were eventually able to prove that this equation is actually true. You see, it's useful to be able to guess numbers in an educated way. So, so now I said, let's see how the guesswork. I already explained how I was able to find Jim's fraction. All right? Any questions? Pretty neat. There are other contexts in number theory with this. Oh, yes, question.
So, the like argue and the algorithm that you found, how you found A1, A2, the first few A1s. Because you first on the algorithm that how you found the sequence.
Yes.
Because you found the difference between the actual value and the approximation at some point, and then you flipped it. So if the number is very big, that means the error between the
If the number or the numerator or denominator? Yes.
The one of those numbers. If
Yes.
that's big,
Yes.
then it means the error between the actual number and the approximation right before that has to be pretty small.
Yes, that's exactly what's happening here. You see, the distance between these is 1 over qn plus 1, and qn plus 1 is at least as big as an plus 1 qn. So when that first term you drop is huge, it's especially close. Yep. Yeah.
If the numbers are when we use a fraction number and eventually it terminates.
Yes.
If we actually try to force the algorithm again, then it's going to look like 1 over 0, which is
Well, so for rational numbers, it'll just terminate, and then you just declare mission accomplished. It's over. But if you wanted to find the continued fraction expansion of pi by using the continued fraction expansion of 3.1415926, at some point they're going to not be the same anymore. So you have to figure out it would be nice, and we'll address this question later, of if you have two numbers that are approximately the same, how could you use the continued fraction expansion of one to figure out the continued fraction expansion, at least the first chunk of the other? Okay. So in fact, let's discuss exactly this issue. So what are the good approximation properties of continued fractions? So first of all, every convergence in the continued fraction expansion is the best rational approximation, is the closest rational approximation up to its denominator. Right? So for instance, 355 over 113, or 22 over 7. 22 over 7 is the best rational approximation to pi with denominator up to 7. Okay. Now, in practice, the more natural question might not be what's the best. Nobody goes around saying what's the best approximation to pi with denominator less than 7. Strange question. Let's say what's the best approximation with denominator less than 100. Okay. So if you ask something like that, you have to be a little careful. Each convergent is the best for up to its denominator. But if you tell me up to what denominator you want, then you have to be a little careful. The continued fraction convergence might not always answer the question. So for instance, for the square root of 3, the best approximation with denominator up to 100 turns out to be 97 over 56, which is not one of the convergence. Now, there's a process, there's a term, something called the intermediate convergence. There's a way to interlace between the convergence additional fractions by a systematic method, and the truly best approximations for all denominators can be found amongst those. So the conversions still help you, even though they might not always be the correct answer. Okay? But you should watch this in the literature. If you read books, some of them make this mistake of saying the continued fraction approximations always give the best rational approximations in this simple sense. It's not, strictly speaking, true. Right? But they certainly help you to find all of them. Now, I mentioned before that the distance between alpha, for irrational numbers, you have infinitely many approximations, the distance between alpha and any convergent is at most 1 over q squared. It turns out that if you take any two consecutive convergents, at least one of them will be within 1 over 2q squared. And in this case, there's even a converse. If you can find a fraction, p over q in reduced form, whose distance from your number is within 1 over 2q squared, for that q being its denominator, it must be one of the continued fraction convergence. So this is, in practice, at least for me, how one can rigorously compute continued fraction expansions, continued fraction conversions for numbers, even if you're dealing with a calculator that has limited accuracy. Because as soon as you get within this distance, and you know every other conversion will do that, every other true conversion will do that, these numbers must be convergent. So for example, if we took pi, say pi is around 3.1415926, here's the continued fraction expansion of this rational number. Now you'll notice, of course, I told you before what the continued fraction is. So you can see that 243 is wrong. It's not correct for pi. It is correct for this number. Well, if you just take the convergence for this approximation and ask if they're within 1 over 2q squared of pi, not of the number that they originally came from, then you find, for instance, the fourth conversion indeed is within 1 over 2q squared of pi, and so therefore the fourth approximation to this number will be a correct initial chunk of the continued fraction expansion of pi itself. Okay? So this is how you can find the continued fraction entries in a completely different way than take greatest integer, flip. All right? So there's good decimal approximations can be used to bootstrap. You can detect where things will still be matching. Right? And if it's not within 1 over 2q squared, I'm not saying it can't be the continued fraction entry, but we'll just try one more and see if you can get it to work. If you can get that to work, that's your hunting license to know that you found the correct continued fraction entry for the original number that you cared about. All right? Any questions? Okay. So let's talk about statistical properties of continued fraction entries. So first of all, with decimals, you have 10 digits. So you might have heard of theorems about, most numbers have every digit appearing 1/10 of the time. With continued fractions, we have the entries in the positive integers. So each entry can take a countably infinite set of values. So we might ask, well, how often does 1 appear in a typical continued fraction, or 2? So forget rational numbers. There are only countably many of those compared to all reals. But so it gives us so before we even talk about how often continued fraction entries are 1 or 2 or 3, I want to point out the fact that you can write real numbers or irrational numbers as infinite continued fractions gives a very concrete explanation of a bijection from set theory. So if you look at the irrationals between 0 and 1, they each have an infinite continued fraction expansion. 0 is the A1, and then all the higher guys are positive integers. And so you have a bijection between the irrationals in the intervals from 0 to 1 and the sequences A2, A3, A4, A5 of positive integers. And each of those A's lies in a countable set, right? 1, 2, 3, 4, 5, and so on. And so the set of irrationals from 0 to 1 is in bijection with the product, countable product of countable set, right? And so in set theory, right, the countable product of countable sets is not only uncountable, but in fact has the exact same cardinality as the real numbers, or equivalently as the irrationals from 0 to 1. So continued fractions give a very concrete realization of this bijection. Anyway, as far as the statistical properties go, so Borel showed in the early 1900s that almost every real number is random in its decimal expansion, meaning almost every digit will appear 1/10 of the time. If you look at the first n digits, see how often is 0 there, or 1, or 2, and then take the limit as it goes to infinity, almost all numbers have each digit appearing 1/10 of the time. And each block of 2 digit appears 1/100th of the time for almost all numbers, and so on. So with continued fraction expansions, we have a countable set of entries, 1, 2, 3, 4, 5. So you can't expect a uniform distribution. But you can still ask, how often is possible? Do most numbers have 1 appearing in a definite proportion of the time? And if so, what is that amount? So Gauss had made a conjecture on this, which was then proved by Kuzmin over 100 years later, which is the following. Almost every real number has every positive integer appearing in its continued fraction expansion, and if the number is k, the frequency with which it shows up is log base 2 of 1 plus 1 over k squared plus k, obviously. And this number is independent of the number you're taking. This frequency is independent of the number. It's like Borel's theorem. Of course, there are counterexamples, 0.1111111 and so on, doesn't fit Borel's theorem, but it says for almost all numbers. For almost all numbers, 1 appears with frequency in the continued fraction expansion, log base 2 of 1 plus 1 over 2. Okay? Log base 2 of 3/2. And so that's around 0.415. So a typical real number will have around 41.5% of its continued fraction integers be 1. And around 16.9% of its continued fraction integers will be 2. And so on. As a nice exercise, prove that the sum of these numbers really adds up to 1. These frequencies do add up. It's a sensible probability distribution on the positive integers. Not uniform. You can't have a uniform distribution on the positive integers, but there's a very definite proportion. So if you took, for instance, the square root of 3 has random decimal expansion, and nobody's proved that its decimal expansion fits Borel's theorem, but its continued fraction expansion certainly doesn't fit the Gauss-Kuzmin theorem, since its entries are eventually periodic. So the Kuzmin theorem doesn't apply to quadratic irrationals. Probably applies to pi, probably applies to the cube root of 2, although nobody's ever proved Kuzmin's theorem applies to a specific interesting number, just like nobody's ever proved Borel's theorem applies to a specific interesting number, even though numerically it sure looks like it's pretty good for most interesting numbers without an obvious pattern in the expansion. Okay? Right. Now, I talked about continued fractions so far of numbers. You can also have continued fraction expansions of functions, if the entries in the continued fraction are themselves functions. And in fact, there's this whole analytic theory of continued fractions, which is really big in the 19th century, and is still used today in numerical analysis. If you look up the term Pade approximations, they're rational function approximations to analytic functions, and in many senses, they're even better approximations than the power series expansion, and they're closely related to continued fraction expansions in functions. Now, I want to point out, so here's a famous example, Lambert computed that the tangent function is this infinite continued fraction, but notice that unlike our examples before, now we're working with more general continued fractions, with numerators that are not necessarily always 1, and we even have minus signs. Okay, so there's variations on what a continued fraction might be, more general than what we saw before. And in fact, this formula is what Lambert used to prove that the pi was irrational. The first proof that pi was irrational, like the 1760s, I think, used continued fractions. Okay? He used this formula to prove that if x is a rational non-zero number, tangent of x is irrational. So since tangent of pi over 4 is 1, pi must be irrational. Okay? And as another illustration of continued fraction expansions of functions, the kind of what's called the anti-cumulative distribution function of the normal distribution from x to infinity, not minus infinity to x. This integral can be written as the Gaussian function at x times this infinite continued fraction x, 1, 2, 3, and so on, the positive integers there. And so, Jim, this is what your thesis was about. Okay? Yeah.
If you say so.
Yes, yes. It was on continued fraction expansions of probability distributions that show up in probability theory. They can express, and these are sometimes give much better numerical approximations. This is the point of your thesis. That at least in the 1970s, computers being the power that they had back then, these gave much better numerical approximations, estimates, than directly computing the integrals themselves. So I want to show you some interesting applications outside of math. So if you play the piano, like I don't, you might have heard of octaves and different intervals of music. So I want to explain using continued fractions where the conventional musical scale in Western music came from. This is not the historical truth, but it's kind of an after-the-fact explanation why it turned out the way it did. So the key thing in music is the notes. You press a note, and the piano being a string instrument, you press the note and you get a vibration, and vibrations that have a ratio that's 2 sound especially pleasing together, right? You want to play notes together. And more generally, frequency ratios between notes that are rational numbers with small denominators sound very good. So 2 over 1, 3 over 2 sound especially pleasing. And so in the Western musical scale, the convention is we want to have our strings set up so that consecutive notes in the musical scale always have a frequency ratio that's constant between any two consecutive notes, no matter where you are on the scale. And so let's call that frequency ratio R between consecutive notes. And suppose we want to set up our scale so that notes that are n places apart have a frequency ratio of 2. So somehow 2 should be realized as a frequency ratio between some pair of keys. And I want 3 over 2 to be realized as a frequency ratio between another pair of keys, some other distance apart, say m notes apart. Well, that means if you pass from one note to another note n places down, you want r to the n to be 2, and then r to the m to be 3 over 2. And if you put these equations together, you need 2 to the m over n to be 3 over 2. You can't solve that in fractions, m over n. But you might be able to approximately solve it. You see, m over n should be a good rational approximation to log base 2 of 3 halves. And so there's the continued fraction expansion for log base 2 of 3 halves. And if you set up the entries 0, 1, 1, 2, 2, 3, and so on, and compute the convergence, so the top number is m, the bottom number is n. The n is connected to a frequency of 3 halves, the n is connected to a frequency ratio of 2. And so for instance, if you had 5 keys on your piano scale, then you might, 5 keys could form your octave, and then notes that are 3 notes, keys that are 3 notes apart would give you your 3 halves. But this is what we use in Western music. The 12-note scale and notes, keys that are 7 notes apart give you the frequency ratio of 3 halves, the so-called perfect fifth, whatever that means. Anyway, so if you look at music theory, in Western music, it's all based on a 12-note scale. This really all developed historically. Okay, nobody was using continued fractions to justify ahead of time how things should be, but it explains why things developed in this way. And if you don't like that, then you can try to do a 41-key keyboard, right, between consecutive C's and nightmare. Anyway, I think that the 3 and 5 are they're used in some other musical tradition, not Western music. I think in Asia. All right, let's look at the calendar. Okay, so a year is not a whole integral number of days long. 365.24219 days. And so if we want to develop a calendar with leap years every so often to account for the lack of consistency between the number of days and the actual rotation of the Earth around the Sun, let's suppose we agree that we want to have a block of Y years among which L of them will be leap years. How should we choose these blocks of calendars and leap years in those blocks? So if you, over this whole period of Y years, with each leap year having 1 extra day, you'll have 365 Y plus L days in total, each leap year adding 1 day. So the average number of days in that block of Y years, 365 Y plus L over Y, 365 plus L over Y, I want that to be a good approximation to the actual number of days in the solar year, 365.24219. So I want L over Y to be a good approximation in rational numbers to this decimal 0.24219. And so there's the decimal as a continued fraction, and here is convergence. Here you see, of course it's not so surprising, that's nearly 0.25. You don't need continued fractions to see that. But the point is that, notice that the very first interesting convergence is 1 over 4, which is exactly the Julian calendar of, in every block of 4 years, have one of them be a leap year. Okay? And that's, of course, that's what Caesar's calendar was based on. But of course, over time, over the course of centuries, from ancient Rome to the 1700s, things got really out of whack, and Easter started to be taking place on a time of year when it wasn't really spring anymore. So there was a decision in the 1700s to Pope Gregory established a new calendar, and let's see how continued fractions suggest what to do. So the denominator is Y, the number of blocks in the years containing some leap years. So every 4 years you have 1 leap year. Now this is ugly. Look at all of these. You don't want to say every 33 years we should have 8 leap years. Who can keep track of that? Actually, the Persian calendar is based on this. But the denominators here, the denominators are not so nice. We might like a nice round number. Remember I mentioned before intermediate convergence? So if you look between 31 over 128 and 752 over 3105, then what you do is you take the recursion for the P's and the Q's, but don't let the A be the entries in the continued fraction, but let them be 1, 2, 3, 4, up to the entry in the continued fraction. And those are the intermediate convergence. And in particular, between these two convergence, at A equals 6, you get the intermediate convergence 194 over 801. Aha! 801 is nearly 800. 8 centuries. Okay, that's a nice round number. We're not going to live for 8 centuries yet. But if we take 194 over 801 and just tweak it down to 800, 194 over 800 is 97 over 400. Aha! You see, that's a slight tweak on 1 out of every 4 years. This says for every 400 years, have 97 leap years. In other words, have a leap year every 4th year, except 3 times. And if you're in a block of 400, let's just cut out the years 100, 200, and 300. And this is the Gregorian calendar, where you have a leap year every 4th year, except when the year is divisible by 100, except when the year is divisible by 400. And then you go back, and so it's when 2000 was in fact a leap year. Okay. And so I'll just end by mentioning 2 quick open questions, very simple. First, here's the continued fraction expansion of the cube root of 2. There's no known pattern for this, okay? But a famous open question is, you see a few large entries, not huge, but prove that the continued fraction expansion of this specific number is unbounded, that the entries can get arbitrarily large. There's no known rule for the entries. This would be a very hard problem, but typical for algebraic numbers of degree greater than 2. We expect that not only should they not be periodic, we know that, but the entries should be unbounded. Forget being periodic, it shouldn't even be bounded. And then, is there any rule for the expansion of pi? Nobody's seen a pattern in that. On the other hand, this is really intriguing. E, 2, 1, 2, 1, 1, 4, 1, 1, 6, 1, 1, 8, 1, 1, 10, 1, 1 even numbers, a little glitch at the beginning there. But there is actually a pattern in the expansion of E. It's not periodic, but it's certainly a nice pattern. But by comparison, pi looks really random, and it seems to fit the Gauss-Kuzmin statistics pretty well. This would not fit the Gauss-Kuzmin statistics. You're never going to see a 5 in the entries at all. Okay? So I'll stop there. Thanks.
Does anyone have any questions?
Yes, sir.
So you couldn't find the pattern for the Chinese calendar eventually?
The pattern for the what?
Chinese.
Yeah, so yesterday was the Chinese New Year. And so I set as a task for myself to, explain what was happening with the lunar calendar for the Chinese New Year, and I ran out of time. So maybe next time.
Any other
Yes?
questions?
Mike?
Yeah, so numbers that have like periodic continued fractions, is there something, like a way to characterize like all of those?
They're the quadratic irrational numbers. Oh, excuse me, I'm sorry. The numbers that are purely periodic? The numbers that are eventually periodic are exactly the quadratic irrational numbers.
Okay.
And among those, you can also classify exactly which ones are purely periodic as well. Yes?
Okay.
Yes, that's the theorem of Lagrange. Yeah, so that's definitely known. So this one will definitely not be periodic for the cube root, but probably doesn't even have a pattern that's just centerable anyway either. Anything else?